All right. Hi, everyone. Welcome to lecture 14. In this lecture, we're going to define the concept of a limit of a function as you let the input variable approach a certain number, I guess. Um, you've probably seen the notation of the limit as x approaches a of f of x, or the limit as x approaches a plus f of x, right? Or the limit as x approaches infinity of f of x. So we're going to define all of these concepts now. And yeah, it's, honestly, I think that this section is almost more of like a complicated introduction of notation than it is like anything, conceptually profoundly new. There really isn't like anything especially new on a conceptually in this section. It's really just like to introduce all of these symbols and have them be meaningful so that we can like use them later on to talk efficiently about the definitions we make, especially for like differentiation and stuff like that. But nevertheless, it's important that we get this out of the way so that we can we can move on and we can use these symbols freely. So the way the book goes about this, which I think is actually somewhat kind of a nice, kind of clever in a way, is that they make this kind of broad definition. So I'm gonna state their definition now. So this is definition 20.1. Let S be a subset of R and a real number, or, well, I guess, yeah, I'll just say. So A can be a real number or it can be plus or minus infinity, with A, the limit of some sequence in S. Okay, which is actually important that A has to be, there has to actually be a sequence of points in S that approaches A for this symbol to make sense. So then, we write the limit as x approaches A along S is how they say it. If F, so if two things are satisfied, so S has to be a subset of the domain of F, of course, and for any sequence xn in S such that xn approaches A, we have the limit as n approaches infinity of f of xn equals L. Okay, so basically, yeah, I mean, we need S to be a subset of the domain of F because otherwise, we can't, it doesn't make sense to talk about F of xn for sequences xn approaching A, I guess. Obviously, if you want to say something like the limit as x approaches A along S of f of x equals L, and S contains some points that are not in the domain of F, then you can at least try to, reformulate the statement by just throwing out the points of S that happen not to be in the domain of F, and then making the statement, right? As long as there's still a sequence of points in S that approaches A, then you're fine. And of course, if there's no sequence in S that approaches A, then it just doesn't make sense to talk about this because, there should be no relationship between the values of F on S and like what the behavior of F near A, I guess, is the point. Okay, so this is a very broad thing because S, in this definition, S can really be like any subset of the domain, right? So it can look, S could look very strange. It could have all sorts of like weird, missing points and dense point areas where there are points kind of clustered together, or like isolated points or whatever. Like who knows what S looks like. But the again, as with like a lot of the things we've been doing so far, the good news here is that we are mostly only interested in cases where S is like an interval of some kind. So that's actually how we make the definitions of the sort of familiar ideas. Sorry, the familiar limits. And I guess I should say that, let's see. Yeah. I don't know, whatever. Yeah, so let's go ahead and just define the familiar types of limits. So this is definition 20.3 now. So we can sort of conveniently use the definition we just made to sort of knock out all of these limits. So for A in R, we write the limit as x approaches A of f of x equals L if the limit as x approaches A s of f of x equals L for some set, let's see, S equals J without the point A, where J is an open interval, right? Oops, is an open interval containing A. Okay, so it's actually implicit in this definition, right, that if this symbol has meaning, right, if this equation is true, and of course, remember, L can be like plus or minus infinity, but if this is meaningful, that requires F to be defined on some open interval containing A. So basically, there can't be like points missing from the domain of F getting like arbitrarily close to A. There has to actually be some radius around A where like all the points within that radius are in the domain of F. Okay? So that's the two-sided limit, I guess you could say. And then, so let me actually, I'm just going to sketch kind of like what this looks like, right? So here, S has to be, if this is like A, then S has to be of the form, maybe it's like asymmetrical. So this interval is J. And then S, right? S leaves out the point A. So S leaves out A. That's important, by the way. Like, we really want to make the definition so that like the set S itself does not include the point A, because that way you can talk about the two-sided limit of a function which might exist even if the value of the function at A is like some random number that is not equal to the two-sided limit, basically. So like in this case, right? if the value of the function is just randomly displaced for no reason, the two-sided limit still exists, even though this value at a is something else, right? So anyway, so that's the two-sided limit, and then the let's see, right, one-sided limits, right? Okay, so this is still 20.3. So B, these are the one-sided limits. Right. For a in a plus if the limit as x approaches a along S of f of x equals L for some set S of the form A, B. Okay, so basically here S is just a set that's like an open interval just to the right of A, right? So just some numbers just above A, okay? So on the number line, that would look like, you know, I guess this is like it's like an open endpoint, right? And so we're sort of approaching A from the right that way, right? So again, F has to be defined on some open interval of this form in order for this symbol to make sense. And then similarly, the limit as x approaches A. This is the right-handed. And then this is the left-handed. Right. So this, if the limit as x approaches A along S of f of x equals L for some set S of the form B A. Yeah. I guess they use the letter C. It doesn't really matter. So basically an open interval, you know, touching A, but to the left of A on the number line, okay? And then one more, the last one here. This is infinite, you know, limits as x approaches infinity. So we write the limit as x, oops, sorry. The limit as x approaches, yeah, sure, infinity. Ooh. Of f of x equals L if the limit as x approaches infinity S. Right. Yeah. F of x equals L for some S of the form C infinity. Okay, so just like an open set going all the way out to infinity, starting at any number C, it doesn't matter. So as long as there's some number C, so that F is defined all the way from C to infinity, and I mean, not including C, obviously. and the limit as x approaches infinity along this interval, according to our previous definition, is equal to L, then we just say the limit as x approaches infinity of f of x equals L. Again, it's like another sort of example of how like we don't care about any of the initial behavior of the function f. We just care about like the asymptotic behavior. So you can make c be as big as you want, and still like if the limit exists on that interval, this this statement would be true, I guess. And then similarly, we would say limit as x approaches infinity, as x approaches negative infinity, sorry, of f of x equals L if, oops, limit as x approaches negative infinity along S of f of x equals L for where, S equals negative infinity b. Okay, right. So yeah, hopefully, I don't know. I don't think there's a whole lot to say about this. As long as you understand the original definition here, 20.1, then hopefully it's clear why these are, the definitions we make for sort of the familiar versions. Just in terms of the original kind of general one, yeah, you'd want for the two-sided limit, you'd want you'd want as an interval around A on both sides, obviously, right? But you just delete the point A. And then for the one-sided limits, you just need an interval on one side of A. And then for the infinite limits, you just need an interval that extends from some point to infinity or from negative infinity up to some point. So that's all. That's all for this section. And then I think in the next one, we'll look at a couple examples and we'll go from there.